You ever stop and think about how massive apps like, say, Instagram or Amazon get built by literally thousands of engineers without just collapsing into a pile of digital rubble? Well, today we're going to pull back the curtain on software architecture. We're looking at the blueprints and two really key tools that keep that chaos at bay. Let's jump in.
I mean, it's a huge question, right? When you have hundreds, maybe even thousands of people all working on one piece of software, how do you make sure everyone's building in the same direction, using the same language, not accidentally tripping over each other's work? That's the core puzzle we're going to unpack. Okay, picture this. You've got one team building a user profile, and they call it the customer account. Cool. But at the same time, another team, the one working on billing, calls that same thing a client record. Then a third team over in customer support calls it a user profile. See the problem? They all mean the exact same thing, but these tiny little differences in language create massive confusion and, you guessed it, bugs down the line. That, right there, is the chaos of collaboration.
So, how do we clean up this mess? Well, the first tool in our Architect's Toolkit is a fancy word, homogenization. But all it really means is taking all those different, conflicting pieces and making them uniform, making them consistent. It's about creating that single shared blueprint that everyone, and I mean everyone, can understand and follow. At its heart, homogenization is just about creating a shared language. When different teams inevitably build things that do the same job, this process is how you bring them all together. You get rid of all the synonyms, you agree on one term, one definition for every single concept. You can kind of think of it as being the official editor for the project's dictionary, just constantly tidying things up.
So how does this tidying up actually happen in the real world? Well, it pretty much boils down to three key actions you take on the code's building blocks, which are called classes. First, you combine any classes that are basically just different names for the same thing. Second, you take any classes that are trying to do way too much at once and you split them up. And finally, you just get rid of any classes that are redundant or aren't pulling their weight anymore. And this, right here, this is the whole philosophy behind splitting those classes. It's really the golden rule of good software design. A class, which is like a little blueprint for a piece of the software, shouldn't be a Swiss Army knife trying to do everything. No, it should be a scalpel, designed for one specific job, and it should do that job perfectly. Let's look at a super common example. So before you do any cleanup, you might have this one big student information class, and it holds everything about a student, their name, their address, but also their entire academic history. This thing is doing way too much. So the solution is to split it. You create a student info class that only handles personal details, and then you make a completely separate transcript class for their courses and grades. Now, each class does one thing and does it really, really well. Okay, so we've tidied up our language, everyone's on the same page. Now, let's talk about our second tool, the building blocks themselves. We're moving from a shared dictionary to shared components. And these aren't just any old bricks. You should think of them more like smart, prefabricated modules that are just ready to be snapped into place. So yeah, this is the formal textbook definition. But what does it actually mean? Well, a component is just a self-contained part of the system that has one specific job. It hides all of its own complexity. But the most important word here is replaceable. As long as a new component connects in the same way, you can swap it in and out without the rest of the system even noticing. It's just like changing a tire on a car. And this whole idea of being replaceable is what makes components so incredibly powerful. It means they're reusable, in totally different projects. It gives you this true plug-and-play capability. You can update one little piece, like your payment processor, without having to shut down and redeploy the entire application. This kind of modular thinking is really the foundation of almost all modern flexible software. Okay, so we have these powerful modular bricks. But how do we see how they all fit together to build the whole house? For that, architects use a very specific kind of blueprint. It's called a component diagram. The best way to get a feel for this is to just build one together. So let's use a simple online shopping system as our example, and we'll reveal it piece by piece so you can see exactly how these different components talk to each other. All right, we'll start with the part that you, the user, would actually see, the web store subsystem. Now, this thing is actually made up of a few smaller components itself. We've got a search engine for finding products, a shopping cart to hold them, and an authentication component to handle logins. This is basically the digital storefront. Now, of course, the web store can't do its job all by itself. When you search for a product, that search engine component has to check if it's actually in stock. To do that, it talks to a totally separate component, the warehouse subsystem. And see that little circle icon? Architects call that a lollipop, and it represents a very specific service being offered. Think of it as a pre-approved question the search engine is allowed to ask. In this case, hey, do you have this item in your inventory?
And for the final piece of the puzzle, when you're ready to check out, the shopping cart component needs to handle the payment. So it connects to our third subsystem, accounting, and it uses that manage orders interface to finalize the sale. And just like that, we have a complete high-level blueprint. Anyone on the team can look at this one diagram and instantly understand the major parts of the system and, this is the crucial part, exactly how they're allowed to communicate with each other. So we've looked at cleaning up our language with homogenization, and we've looked at building with these modular components. But why does any of this architectural stuff really matter? Well, it's all about building software that is designed from the ground up to evolve and to last. And the payoff for doing this work, well, it's huge. Each one of these tools gives you a clear, massive advantage. Homogenization, that gives you clarity and consistency, which cuts down on team confusion and a ton of costly bugs. And components, they deliver modularity and reusability, which makes the whole system way easier to update, to maintain, and to grow. Ultimately, this isn't just about being neat and tidy for the sake of it. Good architecture is a long-term investment. By using tools like these, developers are creating systems that aren't brittle and rigid, but are adaptable and resilient. They're building software that can actually change with the business, instead of having to be completely torn down and rebuilt every few years. And that kind of leaves us with one big question to chew on. In a world that is increasingly run by incredibly complex software, from our phones to our cars to our financial systems, maybe the design, the architecture itself, is becoming the single most critical part of the whole process. Are the blueprints now more important than the individual bricks? It's something to think about.